Well, welcome back. We're coming to you from the Downtown Business District, and today's topic is the test of differences of two population means. This is presentation 9.1, test of a difference between two means. The key concept here is that variances add together. To illustrate our theory, we're going to consider two populations x and y with means 70 and 80 and standard deviations 18 and 20. Now we choose these numbers to make the computation easy and to illustrate the concepts involved. We take samples of size 36 from population X. They'll be normally distributed, cluster around 70, and the standard deviation will be sigma over square root of n, or 3 units, which represents the variability about the population mean. And we do similarly for y. The y bars will be normally distributed, centering around 80, and the standard deviation given by 4.0. Now we systematically look at the differences between the x bars and y bars. So you see them coming on the screen here. We take an x bar and a y bar, and we take several pairs of them. We've got 3 here. And we systematically look at the difference, y bar minus x bar. The idea being here that these differences in y bar minus x bar should cluster about the difference between the population means, or 80 minus 70, or 10. The standard deviation in the variability here, in the differences, is given by the standard deviation squared, the sum of them. These are called variances. The variance in y plus variance in x, or 3 squared plus 4 squared, giving you the square. And applying Pythagoras result, this results in the standard deviation in the y bar minus x bar of 5.0, which is rather strange because the variability here plus the variability here, the variances add together in the sense of Pythagoras theorem, and we're saying that is similar to two independent vectors. Independents mean perpendicular to each other, and the square on the hypotenuse is equal to the sum of the squares on the other two sides. Now we're going to carry out a test. We're looking at a test of non-filtered cigarettes, and this should be filtered cigarettes. We're comparing the two. We take samples of size 32 and 42, and we come up with this result. Now this is one sample, single sample. The statement of the hypotheses, the null says there's no significant difference between the two means, which means the difference is around 0. HA, the non-filtered cigarettes have a significantly greater level of tar, or the difference is greater than 0. Looking at the sampling distribution for n equal 32, we don't know what mu sub x bar is, but we do know that sigma sub x bar is around 0.495, and similarly with y bar, they'll cluster around a certain value, population mean, and sigma sub y bar is 0.494. Now we're going to look at the differences between a y bar minus the x bar, and we're saying that should cluster around 0 since our null hypothesis says the difference between these population means is 0. And here we go, the variances add together. That is to say, this sigma x bar squared plus sigma y bar squared, and the square root of that gives me my standard deviation in the differences here, 0.699. And in this case, if we consider an alpha of 5%, critical value 1.645, we reject x naught, h naught, if your z statistic is beyond the 1.645. Looking at the weight of evidence, the observed difference 16.8 minus 14.3, the hypothesized difference of 0, and on the bottom we have the standard deviation in differences, 3.577, far greater than 1.645. This is very convincing evidence against h naught. The p-value, we're probably getting a z more extreme than 3577, 0.0017. Extremely rare event if h naught were true, so we reject h naught. Very convincing evidence. This is the end of presentation 9.1. We ask you to review once again, take notes, and go to presentation 9.2.